Okay, so today we're going to continue looking at our logarithmic functions. So now, very briefly, we went over what the graph of a logarithmic function looks like. All right, so our logarithmic function was the inverse of our exponential. So, we took a look at just the general shape of, I think this was, log base 2 of x. So very briefly, I want to talk about the transformations that take place, which are the same transformations that take place on our exponential. It's just our graph looks a little different, right? So I can do a horizontal translation if I subtract from the inside, okay? Remember that goes opposite, so minus h would be moving to the right h units, plus h would be moving to the left. We can do a vertical transformation, okay, and we can reflect it the same way. Okay, so if I throw a negative out in front, that's reflecting over the x-axis. All right, so that would be kind of like an exponential, but it would be, we'd still have the same domain, right? I can't plug in our domain for for logarithms has to be greater than 0, okay? You can't plug in 0 to a logarithmic function because you can't raise a number to a power to get 0, right? There's nothing I can raise any number to get 0 as a result, okay? So we can't plug in 0 to logarithms. It has to be greater than 0. So this was our reflection over the x-axis, right? If we did a reflection over the y-axis, it would just be the logarithm on the other side like that. All right, I don't want to spend too much time on that, though. That's pretty straightforward. And we have a plethora of graphing utilities at our disposal now that we are remote. Okay, you have your laptops, you have your phones, you have your computers. There's a lot of programs that you can use to graph. I don't know if I've told you this. Okay, there's a website and an app called Wolfram Alpha, like the two animals, wolf and ram, and then alpha. This is a great tool. You can plug a function into it. It'll graph it for you. If you get a paid version, if you pay for a subscription, it gives you step-by-step instructions on how to solve things. It's a really great program. It's also free. It doesn't do as much for you for the free version, but if you're just using it as a graphing tool, it's perfect. Okay, so those are the properties of the graph. What I want to get into, though, are some algebraic properties. So let's remember some of our exponential properties. If we had two exponential functions, okay, with the same base, a and a here, right? When we multiply those, we add the exponents, right? If I'm dividing a to the x over a to the y, we keep the same base and we subtract, right? So like we've seen, and we can manipulate our logarithmic function to an exponential function, okay, our properties can also be translated into logarithms. So we have an addition and multiplication property. And this, again, goes both ways. If I have two logarithms with the same base, okay, and I'm adding those, well, I can rewrite that as a single logarithm where I multiply what's on the inside. All right, so our addition or multiplication property tells us that if you're adding two logarithms with the same base again, all right, we can combine what's on the inside by multiplying those. Our subtraction or division property, okay, similar like this, if I am subtracting two logarithms with the same base, then on the inside, I can divide. Okay, and then here we actually have another property, okay, called the power property. And that says if we have a logarithm with an exponent, okay, so if I have an exponent like this, I can take this exponent and I can move it out to the front and make it a coefficient. Okay, and like I said, all these are true in the reverse. Okay, so if you had a logarithm like this and for some reason you couldn't, evaluate this or you needed to separate it to solve, you can separate the logarithm into two separate addition ones. Okay. Now this goes true. This is true with our common log and our natural log as well. Okay. Okay. All as long as we have the same base. Okay. So if this was log base 5, or I'm sorry, if this was like log base 5 and this was log base 10, then there's nothing you can do. Those are two separate quantities. All right. We can't combine those. Only if they share the same base. Okay, and then notice, right, the base just kind of tags along with it, right? Just like up here, I'm not doing anything to the base when I'm manipulating my exponents. I'm just worried about the exponents. So let's take a look at a few examples. Oh, why is there an ant? Gross. Okay, so you will either be asked, if it's a problem like this, straightforward, you will either be asked to expand or contract. Okay. So, just a side note, I like using parentheses after the log just to make sure that the base and everything else is separate. Okay. You may not always see it like this. You may see it without the parentheses. I add the parentheses just for kind of for clarification. All right. So I want to expand the term log base 4 of 5x to the third. So the first thing you want to do is either the addition or multiplication, and then after you got everything separated, we apply any power properties that we can. So here, inside, we got multiplication. All right, so we're multiplying the 5 times the x to the third. So we can separate that with addition. All right, so I'm going from a form that looks like this to a form that looks like that. So I have to keep the same base. So I'm going to have log base 4. And the first part I have is 5. Then I'm separating the multiplication. Right? You can draw on the multiplication if you want to show the separation. I'm going to separate that with a plus sign. I have another log base 4. And my remaining term, my other term, is x to the third. Okay. Now this, okay, like I said yesterday, this is just a number. We don't know how to calculate this yet, but eventually we will. This, while I don't have any multiplication going on anymore, I do have that power, so I can apply the power property. So I take this 3 and I just bring it in the front as a coefficient, and then everything else is the same. Right? So these two are equivalent statements. Having log base 4 of 5x to the third is the same as saying log base 4 of 5 plus 3 log base 4 of x. Okay, so that's one way we can manipulate our logarithmic functions. Okay, the other way is they might ask you to condense it. Okay, and condensing usually works in our favor when we're trying to solve. Okay, if we have something to solve, once in a while we'll have to use expanding, but a lot more often than not, we will be condensing. So we are going to condense. Which one do I want to do? No, I don't want to do that. All right, so here we're going to condense 3 ln x minus 4 ln of 4y. So here we're going to do the opposite. So first, I want to get the power property out of the way. Okay, because I can't condense if I have a coefficient in the front. So the first thing I want to do is I want to bring that 3 up to the top here. So 3 ln x is the same thing as ln x to the third. And actually, I'm going to show you in a second with numbers why that's true. And then this, there's nothing in front, so I'm just going to have ln of 4y. So now that the logarithms are by themselves, there's nothing out in front, I can apply any of my rules up here. Okay, so we have subtraction going on. So I'm going to write these as division. Now, like our normal algebra properties, okay, if I'm doing multiplication and addition, it doesn't matter what order it goes in, right? 5 plus 3 is the same as 3 plus 5. 5 times 3 is the same as 3 times 5. So that doesn't matter. If I'm doing the subtraction or the division, order matters. Okay, 5 minus 3 isn't the same as 3 minus 5. We get separate answers. Same for division. So here we have to make sure whatever comes first goes in the numerator, whatever goes second goes in the denominator. So now I have one logarithm. Okay, that's what condensing is. We're going to move everything to one logarithm. In the numerator, I'm going to have x to the third, and in the denominator, I'm going to have 4y. All right, and that would be our final answer, because for condensing, right, my goal is to have one logarithm. And there we have the natural log of x to the third over 4y. Any questions about that? Okay, so before we move on to our last property, and probably one of the most important, I'm going to show you the exponential part. So we'll do something simple. ln of 3 squared. Okay, well, 3 squared is 9. So I can just take the natural log of 9. Okay, so that's 2.197. I'm just going to leave that there. I'm not going to bother writing it down. So our power rule tells us that this is going to be the same as 2 times the natural log of 3. So if I type in 2 natural log of 3, excuse me, we do get the same number. Okay. Same thing if I did the natural log of 2 plus the natural log of 3. Now I'm just doing natural log because it's the simplest one, right? If I combine those, the natural log of 2 times 3, which would be the natural log of 6, again, I get the same value, right? So you can play around with numbers like that to test your properties, but it's pretty straightforward there. Now, in order to solve a lot of these, okay, we might end up with something like this, and I talked about this yesterday. There's no way for us, without the use of, calculators, to calculate this, to evaluate something like log base 4 of 5. And unless you have a fancy calculator, you can't plug that in, okay? Like I said the other day, well, here I have log, so that's base 10, and here I have natural log, so that's base e. Just looking at the calculator buttons as they are, there's no way for me to change a base. I can't take log base 2 of something. I can't take log base 5 of something, okay? If you mess around with your buttons, okay, you might find, is it here? Yep. Okay, this lets you type in a logarithm with its own base. Okay, so here I can do something like that. But again, your more basic calculators won't have this option, or if you have an older calculator. To calculate something like that with only your basic natural and common logarithm, we use what we call a change of base. Let me see, do they call this a formula? So if I have A and B are positive numbers, okay, just like, they have to be just because of the domain of logarithms, I can rewrite this as log of B over log of A, where that is the common logarithm, okay, 10 over 10. Or it's the same thing as the natural log of B over the natural log of A. Or we could use any base. Let me say, all right, but these two are the most common, so we mostly focus on those two. All right, so let's actually take a look at log base 4 of 5. Okay, let's do it with both. So the only thing that we have to be careful with here is make sure that the number that you're plugging in is always the number in the numerator. And your base number is always in the denominator. Right, so I'm gonna calculate all of these, and we're gonna see that they are in fact the same number. All right, so let's say I didn't know how to do that right now. I need to calculate log base 4 of 5. So I could just do log of 5. On the calculator, make sure you close your parentheses. Okay, if you leave it open, then it gives you a really weird answer. Over log of 4. So using our common logarithm, I get that log base 4 of 5 is about 1.16. If I use the natural log, I get the same exact answer. Okay, and just because we have it, I'm going to calculate log base 4 of 5, and we should, in fact, have 3 answers that are exactly equivalent. Okay, so all of these are about 1.161, all right, if we're rounding. Now, to wrap it up, logarithms that don't exactly go into each other, okay, obviously something like log base 4 of 2, that's a whole number 2, okay? If it doesn't work nicely like that, okay, your logarithms are irrational numbers. They will continue forever. They're decimals that go on forever with no repeating digits. So moving forward, if they don't ask you to round, if you don't see round to the nearest hundredth, I would prefer you leave your answer like this. Okay, just like if we're talking about doing like quadratics, I would prefer something like the square root of 2 rather than 1, whatever it is. Okay, because analytically, okay, this isn't very accurate because you have to stop. You're either cutting off numbers or you're rounding, which changes your answers later down the line. Okay, something written like this or something like written like this is more exact because you can type this in and it'll give you the whole decimal. Okay, any questions about our properties?